Hello everybody, this is Mr. Shaban. Today we're going to talk about another unit which is called chemical bonding. And this unit we're going to go through why the atom or element goes in bonding and what are the different types of bonding. In today's lesson you need to know the differences between the following: element, compound, and mixture. Element is a substance which is made from only one type of atom. So we can say carbon is an element because carbon has one type or one kind of atoms. All the atoms of carbon look alike. We can say when two or more elements come together and chemically bond together, they are going to be called compounds. So compounds is a substance which is made from two or more elements that have reacted chemically with each other. While mixture consists of two or more elements or compounds, but they are not chemically combined. So the difference between a mixture and a compound, the chemical bonding. In mixture we have no chemical bonding, while in compound we have chemical bonding. Okay, so let's double check another differences between elements. We have metals, which are elements that react to form positive ion, and we have metals, which are elements that react to form positive ion, and we have non-metals, which are elements that don't form a positive ion. So these metals and non-metals react differently in a chemical reaction. Metals are going to lose electron in order to change into a positive ion, and non-metals are going to change into a negative ion because they tend to gain electrons. This is what we call alloy. So alloy is a mixture of elements. We have the majority, as you can see, is the bigger element, and the minority is the red smaller ones. So alloy is a mixture of metals. These metals are coming together in a certain structure, and this alloy is going to be a little bit harder and giving special properties than the metals. So let's first talk about the structure of the atom. The structure of the atom consists of a core. This core is called nucleus. The core consists of neutron, which is yellow, represented in yellow color, and proton, which is represented in blue color. Surrounding the nucleus we have levels or energy levels. These energy levels contain a red particle which is called electron. So we can say that we have a core. This core consists of two particles, proton and neutron, and surrounding the core or the nucleus we have energy levels where electrons are moving around the nucleus. The word atom came from a Greek word which means cannot be split. So it's the smallest unit which cannot be split. So as we have taken earlier that we have three different kinds of particles inside the atom. We have the proton, we have the neutron, and we have the electrons. Protons and neutrons both are found close together at the center of the atom in a place called nucleus. And electrons are moving around the nucleus. If you want to compare the three particles in terms of the mass and charge, here is the table which is summarizing that for us. This is the mass, and proton has 1, value of 1, neutron has a value of 1, and electron has no value. This means that the proton and neutron are having a value, are making the mass of an atom, while the electron can be neglected. It's very, very, very light, where it can be neglected from the mass calculation. On the other hand, when it comes to the charge, the proton has a positive charge, neutron has no charge or uncharged particle, and electron has a negative charge. So when you compare between the three particles, we can say that the mass of the proton is 1, neutron 1, or we can say that the two particles which are contributing or building up the mass of an atom are the proton along with neutron. While electron can be neglected because it has a very, very small value. So when it comes to the charge, proton, it's positive, neutron, no charge, and electron takes a negative charge.
First, why do atoms do this at all? Well, like everything else in the universe, atoms do whatever they can to reduce their overall energy. And they reach their lowest energy by achieving a balance between attractive and repulsive forces, being neither too clingy nor too aloof. So when two atoms approach each other, the electrons of each are attracted to the protons of the other. This is the electrostatic force. Like charges repel, opposites attract. Like in real life, or at least Paula Abdul songs. I know, I'm old. So when one atom is attracted to another, just like Edward Cullen and Bella in chemistry class, to use a slightly more timely reference, it gets stressed out by the attractive force and tries to relieve the stress by getting closer. We've all been there, right? That hot, nerdy vampire girl in your chemistry class, it's intense. The pull is so strong that the stress level or energy rises when the two are separated, so they stay close. But sometimes they can get a little too close. When that happens, the nuclei repel each other because of their like charges, and the energy between them rapidly increases, and they both back off just enough to find that perfect little distance between them, and everyone relaxes. This ideal, wonderful distance is the bond length. It's the distance between two nuclei at the point of minimum energy. In other words, where the attractive and repulsive forces cancel each other out. The distance at which these two atoms of chlorine reach their minimum energy, caught between the attraction of the electrons to the nucleus and the protons repelling the nuclei, is the bond length. That energy minimum, which we know absolutely is negative 239 kilojoules per mole, occurs when the distance between the atoms is 0.00199 nanometers. That distance is the bond length of Cl2, chlorine gas. Now, because the electrons are attracted to both nuclei in the molecule, they actually spend the majority of their time in the space between them. This is often described as sharing electrons, and we call this kind of bond a covalent bond. But not all sharing is equal. I should know, I have an older brother. The strength with which an atom holds shared electrons is called its electronegativity. The electronegativity of various elements are all super well known and waiting for you in tables on the internet. If two atoms in a bond have very different electronegativities, like say hydrogen at 2.1 and oxygen at 3.5, the electrons are more attracted to the atom with the higher electronegativity. The difference is so great that the electrons spend most of their time around the stronger atom and much less time around the other one, like how all of the neighborhood kids wanted to hang out with John, my older brother, because he was more charismatic. When the electrons hang out closer to one side of the bond, it creates a slight negative charge in that area and a slight positive charge around the other atom. This separation of charges is called polarity. And it's the polarity of the molecule that these atoms form, H2O, that makes water the most important molecule on Earth. Covalent bonds like this, where electrons are attracted to one atom more than the other, causing a separation of charges, are called polar covalent bonds. But when a covalent bond forms between two identical atoms, like the two chlorine atoms in our graph earlier, the electrons are distributed evenly. We call this a nonpolar covalent bond. But you've also got to consider the middle option, where the atoms aren't identical but have very similar electronegativities, like hydrogen with an electronegativity of 2.1 and sulfur at 2.5. The difference here is so tiny that the electrons are pretty much still evenly distributed, and we call that a nonpolar covalent bond as well. There's a huge world of important chemicals that have these kinds of bonds, so many in fact that we will dedicate a couple of separate episodes to them. Covalent bonds tend to form from nonmetals and sometimes metalloids, those elements that have both metallic and non-metallic characteristics. That's because most of them hold their electrons so tightly that they're more likely to share them with another atom than to gain or lose them altogether. Metals, on the other hand, have loosely held outer electron shells, so they're constantly dropping electrons and becoming positive ions. And when positive ions come across negative ions, like those formed from halogens, for instance, you have to know what's gonna happen. They're attracted to each other, which means energy is required to keep them apart, which means that they're gonna bond if they can, creating that oh-so-wonderful point of minimum energy. This type of bond is unsurprisingly called an ionic bond, a bond formed between a positive ion and a negative ion. Because the ions are formed when one atom loses electrons and the other gains them, we often say that an ionic bond is formed by the transfer of electrons from one atom to another. And we can calculate the amount of energy that exists in a bond between ions at a given distance using a formula called Coulomb's law. Note that this only works for ionic bonds because the calculation requires the charges of the ions, which of covalent bonds don't have. Coulomb's law says that the energy between two ions equals the product of the two charges, which are represented by capital Q's, because why not, divided by the distance or radius between the two nuclei, all multiplied by a constant. 2.31 times 10 to the negative 19th joules per nanometer. Of course, the radius also has to be expressed in nanometers, you gotta make the units match. Let's see how it works with something simple, sodium chloride or table salt. We know that the normal charge on sodium ion is +1 and the normal charge on chloride is -1. These are Q1 and Q2. The length of a stable NaCl bond is 0.276 nanometers, so we put that in for the radius. And finally, a quick calculation tells us that the bond contains -8.37 times 10 to the negative 19th joules of energy. Remember that negative number represents a decrease in the energy of the system due to an attractive force, which certainly makes sense here. Sodium and chloride ions are strongly attracted to each other due to their opposite charges. Of course, you might have noticed that -8.37 times 10 to the negative 19th joules looks like a tiny number, but keep in mind we're talking about one single pair of ions. The -239 kilojoules that we got for chlorine, that was for a whole mole of molecules. When multiplied by the 10 to the 17th or so ions in a single grain of table salt, and then by the thousands of grains of salt in a mole, the energy becomes much more significant. The NaCl bond is in fact quite strong. And because they consist of a positive ion and a negative ion, two charges completely separated between two different particles, ionic bonds are extremely polar. Way more polar than polar covalent bonds. And so those are our three types of bonds. Nonpolar covalent, formed by the equal or nearly equal sharing of two electrons between nonmetal or metalloid atoms. Polar covalent, formed by the uneven sharing of electrons between two nonmetals or metalloids. And ionic, formed by the transfer of electrons from a metal to a nonmetal. It's important to remember though that there aren't only three designations for chemical bonds. Just like human relationships, bonds don't always have really well-defined boundaries. Everything is a continuum. Labels are useful, but they can only take us so far. There are, however, certain properties that each kind of bond tends to have that you should know. For instance, ionic compounds are often crystalline in their solid form because of the way the ions pack together, like salt is. They're generally soluble in water because the two ions interact separately with the positively and negatively charged areas on a water molecule. And once they're separated or dissolved, the ions allow the solution to conduct electricity. Covalent compounds, on the other hand, tend to be softer solids, liquids, or gases like Cl2 is at room temperature. They're often not soluble in water, and even when they are, the solutions don't conduct electricity. The difference in these properties stem mostly from the differences in their polarity.